Well, I hope you're all surviving our little blast of winter. The good news is that apparently it's going to be warm this weekend, so we'll get to walk through big puddles as all the snow melts. Lab 2 is due tonight, and just a reminder to get started on Lab 3 because it's going to take a little longer than the other labs have so far. In particular, there's an optional multiplier part. Many people well, I just recommend that you work on the multiplier too because the points you can earn there will loom larger at the end of the semester, and you'll be glad to have gotten them now. So today we're going to have a little fun. We're going to experiment with a more complex digital circuit and think about different ways of implementing it that achieve different goals. So as an engineer, when you're designing something, particularly a digital system, your customer may have different ideas about what it is they want it to be, to achieve. Performance always seems to loom large. And in fact, for many years, sort of digital systems, computers, for example, the main goal was to build them faster and faster and faster. And even though we always have a need for speed, nowadays we start being concerned like, will it run all day on a battery? So power starts to be a consideration. And then finally, there's size. And so obviously if you need 18 chips to implement something and your competitor manages to squeeze it all onto one integrated circuit because they've been much cleverer about the circuit, you can implement things. You can be very competitive by dealing with size. And I'll show you an example of that a little later in this lecture. Okay, so the problem we're going to work on, sort of as our stalking horse, is binary multiplication. So we're going to have two unsigned operands, each of n bits. And if we take two n-bit numbers, unsigned numbers, and we multiply them together, we will get a 2 n-bit product. In other words, the product will be twice as large as the two operands. And when the two operands are the same size. And we can sort of see here, if you just do some mental arithmetic about taking sort of the two largest unsigned binary numbers and you multiply them together, and you can sort of figure out what the numeric size of the product, and then you can sort of see that we're going to need 2 n bits to fit in all the possible results that we get. So that's the problem we're going to work on. It turns out that for small multipliers, like even a 1-by-1 multiplier, the hardware isn't too bad. But for those of you who've already made a start in Lab 3 and are puzzling a little bit over how to build a 32-bit by 32-bit multiplier, you quickly come to the realization that that's a lot of hardware. I mean, there's lots of partial products to create and lots of adders needed to add them together, and your fingers are getting shorter as you type them in. And it can pay to think a little bit about the problem and find out if there's a way of structuring it so that we can build building blocks and then perhaps use the building blocks to actually assemble the final unit. We may end up with much less total work, even though we'll create the same amount of hardware. We'll do it in a structured way where we'll let sort of reuse of a basic building block stand in for just typing a lot of hardware in gate by gate by gate. Okay. So the first thing we're going to do is to spend some time thinking about the structure of multiplication and see if there's some way of dealing with multiplication that allows us to say, oh, I can decompose a big problem into a collection of smaller problems. And if I can do that, then I have a way of, I can try to make myself a set of tinker toys that I can sort of plug together in a hierarchical fashion. So let's suppose that we have n-bit by n-bit multipliers here. So we have something that will take two operands A and B and produce this 2 n-bit result. So let's just, for the sake of argument, say those are what's in your toolbox. And now somebody comes and asks you, can you solve a problem with twice the size? In other words, if I start off with 2 n-bit operands, which will produce a 4 n-bit result, is there a way of thinking about the problem that allows me to use the building block I actually have been able to check out from the stockroom? And in fact, there is, and you're of course quite familiar how to do, big multiplications using, just that little multiplication table that you learned a long time ago. And the way you do it is you decompose the problem where you're sort of taking one digit at a time down here and one digit at a time down there, and doing a table lookup in your head to say 7 times 5 is 35, so I write down 5, carry the 3, so forth and so on. So slightly more abstractly, what we can do is to break down. So each of these A's and B's down here can be thought of as really two n-bit numbers concatenated. There's the low half, and then there's the high half of the number, each of which is n bits large. So each of these little squares here represents one of the n-bit operands that we already know how to deal with. And this is a diagram that shows us how to break the 2n times 2n multiplication into a series of sort of, block by block. If you thought of each of these guys as, if you will, a digit, the thing that we can deal with, the thing that we know how to implement. In our case, it's the multiplication table, but in this case, it's n-bit multiplication. You can see we can parlay that skill of being able to do an n by n multiply by basically breaking this big problem down into 4 subproblems, which will create these 4 partial products. And so one way to think about this is I can use 4 copies of this building block to deal with the A low and B low and A high and B high operands as n-bit operands. And then I'd simply have to worry a little bit about the appropriate scaling, moving things over. So think of this as, this partial product is shifted over by n bits. It's like multiplying it by 2 to the n. And you do that quite naturally when you do a multiplication. Each partial product, as you move across the bottom row doing your multiplication, you're carefully shifting these partial products over by 1 column, representing that, the fact that one of the operands which you dealt with as a digit is really some digit times some number of powers of 10. And then when you write down the partial product, you shift that partial product over by that number of powers of 10. And it's now all lined up just the way it should. So I don't need to reprise multiplication for you. But this is just sort of a diagram that shows how to break a big multiplication problem into a series of small multiplication problems. So what we're going to do is say, okay, that I understand the structural principle. Let's actually roll up our sleeves and fool a little bit with the actual hardware. So if we're going to start our basis, we could start with sort of a 1-by-1 multiplier. And if we think about the 1-bit multiplication table, we build a little truth table like the one you see over here on the right-hand side. And you look at that and say, well, 0 times 0 is 1. In fact, 0 times anything is always 0. And then the only interesting entry in the table is the 1 times 1 entry, which produces a 1. So you say, okay, that's the truth table for a 1-by-1 multiplication, which, of course, as our friend noticed, is actually just the truth table for an AND gate. So it turns out that doing a 1-by-1 multiply is not terribly complicated in the world of binary arithmetic. We can implement the multiplication using a single AND gate. And it produces, well, in this case, we only get a 1-bit result, but in general, when you multiply 2 operands of a certain size, you produce a result which is twice the size. And the reason why this little special case rears its head is because of the special properties of multiplication by 0. Everybody else would have, multiplying by bigger numbers tends to produce the 2 n-bit results. We just don't happen to see that in this table. Of course, you can say, well, that's a very simple basis. And as we'll see, starting here will get the point across, but we'll look at some of the hardware that we're creating and say, that doesn't seem as efficient as I would hope. Couldn't we do a better job? And the answer is almost certainly. And in fact, if we start with building blocks that are slightly more complicated, like a 2-bit by 2-bit multiplier, all the same structural story that we're going to tell works just fine, but we'll use gates a little bit more efficiently. Okay, so whatever starting place you'd like to pick for your own multiplier design. And it's interesting to contrast the write-up in the lab, which is more like the decimal multiplication that you know from your days in elementary school, with the approach I'm showing here. And sort of two different ways of looking at the multiplication problem. I think you'll discover that this way will provide you with some insights that are hard to get from the more old-fashioned way of thinking about the structure of multiplication. Okay, so far we have a 1-by-1 multiplier, and we've discovered it's an AND gate. Okay, so here's how we do this induction step. So, now we say, look, I've shown you how to do 1-by-1. If you give me 2n bit by 2n bit multiplication, how do I go off and do this bigger, or if you give me n by n multiplication, how do I do this 2n bit, deal with 2n bit operands? And, as I explained in the previous slide, we simply break the problem up into high half and low half and think of this bigger multiplication as a set of 4 n-bit multiplications that we already know how to do. And notice what I've done is I've slightly rearranged the order of the partial products. And there's nothing very substantive in the rearrangement. I've just chosen to build something that puts the block in a different order. We still have, every bit is in the same column it used to be in. We've just organized the bits so the columns are listed in a slightly different order. And there'll be a reason for that, which will become apparent as we look at the next layer of structure. Okay, so if everybody's sort of happy with this brick view of multiplication, where we stack the bricks a little differently just to produce a slightly more compact picture. And since we're going to be using it several times, what I'd like to do is to just make sure we... Okay, so this is low, low, and this is high, high, and this is low, high, and high, low. And it doesn't, the order of these two isn't terribly significant, but it sort of gets the point across. Everybody, so just keep in mind that organization of the partial products. This is slightly, you're saying, what's wrong with the old way? Yes, sir? Well, okay, so if I'm going, you mean in terms of? Okay, so suppose I know how to do, so 1011 and 1100. Suppose I want to do that multiplication just in base 2. Okay, so let's do it the old-fashioned way. Okay, so 0 times, so that would produce 4 zeros. And this one, I'm going to now do this digit, and you can see it's already shifted over by a power of 2, right? So when I write down the partial product, which is this digit times the top operand, I'm going to shift it over just like we always have done. So this would be 0, 0, 0, 0. 1 times this is equal to 1101. And then finally, again, 1011. Does that make sense? Yeah. So that's just, so what I'm going to do now is to just take those numbers, okay, and
I just don't see how that corresponds to that block diagram.
To this block diagram here.
Yeah.
Okay, so so think of this, so you're happy with this as sort of a basic picture, right? So think of this as, suppose I had done it, broken it up this way. So that's sort of the next step in thinking about it, right? Okay, so what I want to do is to think of this problem as really 4 different pieces here. What are the 4 problems? I have 0, 0 times 1, 1, right? And I have 0, 0 times 1, 0. And I have 1, 1 times 1, 1, right? And I have 1, 1 times 1, 0. Whoops. 1, 1 times 1, 0. Does that make sense? Yeah. Okay. So I can compute each of these using my building blocks, because that's what I was given, right? And what we'll discover is that I'm really, and then I can take the 4 partial products here. Okay, and if I think about how they're supposed to line up, we'll discover that I can draw the picture either this way, Okay, or I can just rearrange that picture like so. That is, I'm not sure if I'm addressing your.
That makes sense. I just don't. So, like, how would you physically put those numbers in that fashion?
Okay, so let me just, so this is the low one here, right? So this is low times low, right? This is low times high. This is high times low. And this is high times high. I've just labeled the partial products. And then if I actually wrote out those digits, okay, and just simply, you just lined up the columns the way I'm showing here, you would end up with exactly the same answer as we did over here. Okay, so this is slightly weird because instead of just doing the problem from scratch, like we did here, what I'm doing is I'm assuming I have a building block of half-size operands, and now I'm figuring out how to use that building block to do the next bigger problem. Okay, so what we're going to do now is we're going to use this basic structure and say, if I have something of one size, how do I do the next size up? If I have something of size n, how do I deal with 2n? Or if I have something of size 2n, how do I deal with products that end up as 4n bits? So here's a bigger problem, okay, using our induction steps that we've had before. And you can see that the resulting picture, okay, has the same basic form as this has. And each of the pieces at the top level that looks like one of these. So you can see this is the top block and the two blocks side by side in the bottom block. And what we've done now is simply to show you these two levels of hierarchy all pieced together. And you sort of look at this and you sort of go, okay, I mean, this is a very strange way to think about multiplication, perhaps. But it will make more sense as I'm going to squeeze these blocks together in a second. I'm trying to show you first the structural argument, and you can say, does this really compute the same answer as the other one? And in fact, it does. And perhaps this view here would be a little bit more easy to see, because if you think about the diagonals here, look at the diagonals. This is, A0 times all the B bits, and A1 times all the B bits, and A2 times all the B bits, and A3 times all the B bits. Or maybe this diagonal makes more sense. This is B0 times all the A bits, and this is B1 times all the A bits. Right? So, so this is just exactly the picture that looks like here. I've just drawn the order of these things in a way that maybe not the order that you would have picked up originally. Yes?
So just to make sure, the rightmost column would be just B0, then after that it would be B1 plus A0 plus B0.
No, so this is meant to represent the 2-bit product of A0 times B0. Right, so when we write A0, B0, it doesn't mean the bits A0, B0, it's actually the product of A0 times B0. Okay, for some size operands A0 and B0, does that make sense? Okay. Right, so each of these blocks represents a partial product. It's the result of a multiplication using our building blocks. Yes?
So then the rightmost digit, of the result is going to be the rightmost digit of the product of A0 and B0.
Right, and if you think about that, the rightmost bit of the result is the low order bit of the partial product that was formed by A0 times B0. Right, and you can say, why? I mean, this you learned a long time ago. What was the advantage of arranging things in this way? Well, I hope you can sort of see structurally that what I'm doing is if you can imagine that I give you a bunch of n-bit multipliers, if you arrange things in this way, you can quickly build yourself, what we call a brick wall, of these building blocks to build larger and larger multipliers. And once you have your basic circuit, you can just keep iterating these larger and larger units. It's not like you have to keep designing more and more circuitry. Okay, so chapter 1 of our little multiplier cookbook is this sort of view of multiplication. And when you think about it, there's two pieces here. One is I have to form the partial products, so all the multiplication that goes on here. And then secondly, I have to add up all the columns of bits. So step 1 was forming each of the partial products, and step 2 is actually writing down the sums of all the columns. So multiplication, of using our building blocks, and then the summing of the partial products, a two-step process. So one thing that's going to be useful to us as we think about our hardware choices is to say, well, how do we, as we make n bigger and bigger and bigger, what can we say about the cost that we're incurring? If I double the size of the operands, how does the size or latency or throughput of my circuit change as n changes? And what we've done in computer science, because it's sort of an abstract notion of the complexity of a circuit, what we do is we've invented this order of notation, and you can see this is capital theta here. And order of is giving us a sense of how it grows, sort of ignoring the little details, the little constants. And so if I can say something grows linearly or something grows quadratically, those two have quite different hardware costs as I double the size. Okay, and I'm not particularly I don't need to tell you a whole lot about the exact equation to compute the hardware costs from the size of the operands. I'm just trying to give you a feel for how those costs grow as the operands get bigger and bigger and bigger. Sort of a qualitative sense of what happens. And so the order of here's an example right here. Here's a detailed formula, and we say, well, how does that formula grow as n gets bigger? And as I add a little bit to n, and then I say n goes from 1 to 2 to 4 to 8 to 16 to 1 million to 2 million to 4 million, give me a sense of how it's growing. What I would say is that after a while, as n gets very big, there's one term in this equation that dominates. Right? It's the one that really determines the value. So if you think about, a billion squared plus 2 times a billion plus 3, well, the plus 3 hardly makes any dent in the answer at all. And even the 2 billion there, it doesn't matter, because a billion times a billion is most of the answer. Right? So we say that the order of growth of the size of the result of if this was an equation for the size, the order of growth for the size would be order n squared. Right? And there's a little mathematical thing here that shows what we mean. It's bounded both above and below by n squared. So for particular constants C1 and C2, the value of this equation is always greater than C1 times n squared and less than C2 times n squared for almost all n. It's not true for very small n, but for finitely number of n, we might violate that inequality. But there's a lot of possible n's, a lot of integers. And for almost all of them, all but finitely number of them, we can pick C1 and C2 so that inequality is true. So that'll give us a way of a little shorthand. It's like a little EPA sticker on the window of our circuit that gives us a quick glimpse as to the space required or the amount of hardware required or the latency or the throughput. So what we're going to do is start thinking about the hardware costs and the latency and the throughput of these circuits. And we're going to actually use our pipelining skills from the previous lecture to build a whole variety of multipliers that achieve different design goals. Okay, so we can count up the number of things. We have n squared partial products. The widest adder width, if you looked across here, is 2 times n. And so forth and so on. And so the total hardware cost is the sum of all this, and we can come up with sort of a complicated formula here if we want. But in general, what we want to do is to say, look, if I have an equation that involves an n squared term and some n terms and some constants, that the hardware cost is on the order of n squared. In other words, as I would double the size of my operands, I would expect, sort of naively, if these are indeed the hardware costs associated with our hardware picture, I would expect to quadruple the amount of hardware that I need. Right? Because 2 squared is 4. Everybody sort of happy with that? So this is just a way, a quick sort of, give you a quick overview of how many, in this case, pieces of hardware we need to build a multiplier. And you might say, well, look, if I have the AND gates are forming the partial products 1 bit at a time, and I have n squared of those, and then I have all these full adders. I need a lot of each individual building block here of adding together bits in a column. I'll ultimately need about n squared of those adders. So it would seem like if I had to put the data through all of that, maybe the the time it takes for my multiplication circuit to run is n squared. And if you think about how you did it, you can see how as you were thinking about the number of things you wrote down here, you wrote down about n squared things given the n-bit operands. Right, so that gives you a sense of how long it might take to actually do the problem. Now at this point you might say, well, gosh, this is lots of machinery we're inventing here. We must be getting someplace interesting, although this all seems to be a rehash of second grade right at the moment. And you could say, isn't this sort of a, how can I do better than that? Could I get a multiplier that has less hardware cost or higher throughput or better latency? So that's really what the problem we're trying to set up is that problem. Yes, sir?
Does this multiplier actually have n squared latencies? I feel like the longest path through it is like quarter of that.
I think if we look at the next couple slides, you'll be proven exactly correct. So the naive analysis, sometimes we have to be a little careful, and in fact we're going to spend a slide or two being careful and come up with a different number. But good insight, and we're getting there slowly. So the first observation is that treating this as two separate problems, a problem where I have to build partial product circuitry and a problem where I have to build adder circuitry, we might be able to get a better insight about what building block, and so that seems to require at least a couple building blocks. What I'm going to do is suggest that, look, it looks like we have a full adder for about every partial product. Maybe we should combine the two. Maybe we should make a building block that actually thinks about everything that needs to be done and building a building block that goes from the operands to the answer sort of as quickly as we can. Okay. So instead of building circuitry that does the partial product, creates the partial products, and circuitry that does the addition, we're going to build a building block that sort of does a little bit of both and then wire them up in a way that causes us to solve the multiplication problem correctly. So we're going to build a single building block, one of these building blocks here, which is a combination partial product generator and also deals with the addition in the columns as we go down, right? So think of this building block as taking in 2 bits from the columns above. So the two bits of whatever the sum is. It has a carry in and a carry out from carry in from the columns to the right, and it will produce a carry out to the columns at the left, and it will produce some bits out, right? So in general, what I'm going to do is multiply A times B to come up with a 2-bit result. I'm going to add it to those bits of the partial product coming down from the top, and with a carry in from any carry outs of previous things to my right, operations in bits with less significance, arithmetic significance, and I'm going to produce a 2-bit sum and a carry out. So here's a design. So notice that we basically have the 2 operands sort of coming in diagonally, and then the carry in from the bits of lesser significance, the carry out to the bits of more significance, and then the 2 bits from above and the 2 bits below. And here's a little piece of circuitry involving the full adder building block. So the full adder thing is something that you've experienced in Lab 2. It adds together 2 bits and a carry in, so 3 incoming bits, and produces a sum and a carry out. Okay, so this is our little building block, like so. So this is really the only thing where you actually have to do circuit design. And now we're just going to figure out how to sort of piece these building blocks together to form the actual resulting multiplier. This is not the most efficient thing. Here I have a full adder who has a constant input. And you say, well, couldn't I redesign that? I don't need quite as many gates as every gate in a full adder, because in some sense I'm only adding together 2 bits. And the answer is sure. There's lots of little optimizations here, which you may have fun doing. But we're really just trying to get to the larger point about how the structure of the problem can be exploited to achieve certain ends, which I'm about to get to. Okay, so now we get to the question about latency. And you might say, well, there's n additions, and it takes, so I have to add together order n different partial products, and each one has about order n bits in it. So maybe if I go off and imagine how long it's going to take to do this, it might take order n squared. And we can sort of say, well, so look, it's I have n bits vertically, n additions to do, and then I have n bits across. Okay, and so that would suggest that maybe it's n times n is how long I have to wait. But if you think a little bit about how this works, you can see that the actual propagation of information always is down and to the left. So some bits are going down and carry bits are going to the left. It turns out the longest path you can find through this circuit, if you sort of look bit by bit by bit, is every time you take a step, and it doesn't matter which path you follow, the carry path or the sum path or some mixture of the carry and sum paths, you're either moving to the left by one or you're moving down by one as you exit the block. Right? And you can only move left n different times before you get to the end of the arithmetic problem, and you can only move down about n times before you run out of things to add together. And so it means that the total path is somewhere around 2n. It's not n squared. Does that make sense? Do you sort of see why this is your insight, right? Which was that somewhere around order n is a much better estimate of the actual latency here. Okay, and the answer is, another way to look at that is to, what happens is that, well, I won't try to confuse the issue any further. Is that, everybody sort of happy with sort of the order n as the latency of this circuit? Okay. Okay, so this brings us to, a slightly more accurate picture. If we're going to use this hardware structure, and now we've been pretty specific, it still takes about n squared pieces of hardware. The hardware cost is about n squared because I have n squared building blocks, right? N squared of each of these little guys. And then each guy has constant cost. Has one full adder, or two full adders and an AND gate. So the hardware cost for each block is constant, and I have about n squared blocks. So the hardware is n squared. The latency we just saw on the previous slide talked about it being order n. And the throughput, because this is a combinational circuit, is 1 over the latency, or 1 over n. We produce one answer every n time units. So this was, a long way around the barn to get to maybe a result that it wasn't too surprising to you. But I wanted to set up this structure because now, in quick order, we're going to be able to do some pretty interesting things with this structure that will allow us to put up remarkably different stickers here, our little EPA stickers about costs and mileage and throughput and latency. We're going to be able to redesign our circuit using some interesting observations that we're going to spend the rest of the lecture making. Okay, and this was a pretty naive implementation. There are lots of tricks you can do, which you can learn about in other courses, that sort of make the hardware twice as small. So that doesn't change the order of the cost of the hardware, but it does reduce some of the constants and makes a big difference. Okay, suppose we have lots of multiplications. Suppose you have to do not one multiplication, but you are dealing in a digital signal processing environment where you have to do millions and millions and millions of multiplications. You're taking in a stream of audio and you're slowly converting it into MP3, and that involves polytone filters and FFTs, and you have a lot of multiplications you need to do. Can we do better from a cost performance standpoint? In other words, can we, for instance, either get better performance? Can I, rather than having to wait, getting a throughput of 1 over n, can I get better throughput? Another thing is maybe I can use less hardware. So those are the things we're going to think about. Okay, so we know how to do pipelining. Okay, so your next task is remembering our lecture on pipelining, and just think of this now as an abstract electrical circuit. Forget the fact that this is really doing multiplication. Just think about how I would draw my arcs across this diagram to break it into something that would have better throughput. So here's attempt 1. Thoughtfully labeled stupid pipeline tricks, because it's probably not our best choice. If I think about pipelining, this is a perfectly legitimate pipeline. The arcs are going, all the way across, from one side to the other, going across all the outputs, and so this is all fine. Okay. what is the latency and throughput of that pipeline circuit? Well, there's n pipeline stages because I basically broke each one of the n rows here into a separate pipeline stage. The clock period is order n because remember I have to get the carry chain all the way across this whole set of additions. And remember there's a carry out from this guy that becomes the carry in here. So the long path here comes in at the low order block, and then the carries have to propagate all the way through. And the longest such row is 2n. So we have basically order n TPD for in the worst case for the row that takes the longest time. So that means that the clock period is order n. We still have n squared hardware. Think of this as really just adding 2 registers to each of these blocks, or just registers on these 2 output bits. And so that means I've gone from a hardware cost of 2 full adders and an AND gate. I've just added a little, that constant is now a little bigger, but it's still a constant cost. So given that I have n squared blocks, I have order n squared hardware. The latency is n times the clock period. I have n pipe stages times a clock period of n gives me an n squared latency and a throughput then of 1 over n. Because I get 1 answer every clock period and the clock period is order n. So I've done a lot of pipelining, but I actually haven't changed anything. The hardware cost is the same, or at least in order of notation. I've sort of added a lot of registers, but in terms of order of, I've not made the hardware cost any different. But I haven't achieved anything either I've made the latency longer. The latency is now n squared instead of order n, but I haven't achieved better throughput. So this is, you can say, oh, that was pipelining, but it didn't get the job done. And the problem is this order n cost in each pipeline stage. I know, I'll break the carry chain this way. Here's my picture carefully showing a bunch of arcs. Well, this is just stupid, okay? This is, I love this word, stupider. This is not a well-formed pipeline at all. I love him. Such a jerk, Okay, so here's a path through through the circuitry, the sort of sum bits in this column, in which it sees no registers, and the next one sees umpteen registers. This is just not a K pipeline. So it is possible to draw lots of arcs, but we have to remember to be good about drawing arcs that actually get the job done. Hi, Mom, I'm in lecture. Could I call you back later? Okay. Okay, so what we're going to do is we're going to pull the diagram apart in a slightly different way. And what you can see is I've sort of split the diagram apart along the diagonals, taking into account the fact that, remember I had how information sort of flows down and to the left? Well, what I've done is I've exposed the down and to the left arcs. And in some ways so this arc here, which usually just went to the left, is now down and to the left. So this is exactly the same picture. I've just stretched some of the wires. And now what I'm going to do is to start drawing pipeline stages like so. And a miracle has happened. Okay? Think about the latency and throughput of this circuit. Okay, and we're going to show the sticker on the next page, the EPA sticker for this circuit on the next page. But this circuit has remarkably different performance characteristics than anything we've shown so far. Okay, so what is the clock period that I have to use? Okay, and what clock period can I use to clock the pipeline registers here? In other words, what's the longest combinational path from one of these registers to an output register? Well, you think a little bit, right? We have bits that are coming in, okay, and there's a path, okay, that goes from one side to the other, but the longest path is basically constant. In other words, as I make the number of operands, if I make n bigger and bigger and bigger, these diagonals get bigger and bigger and bigger. Right? But I split things along the diagonals. So everything grows this way, and I add more pipe stages, but there's sort of constant time here. So this is the clock period here is constant. It doesn't, as I change the size, if I go from 32-bit multiplications to 64-bit multiplications, I don't have to I use more hardware. Okay, it will take me more cycles of latency to get the answer, but I won't have to change the clock period. So there's sort of a constant path here that's independent of the size of the operands. Okay, so we have order n stages. So if I doubled the size of the operand, I would have, more arcs I would have to draw, roughly linear growth there. The clock period is constant. Okay, it doesn't grow as n at all. The hardware cost is still n squared. I haven't changed the hardware cost at all. The latency is now n times 1, so I'm back to the original latency of my combinational circuit, which is good because you sort of like to say, can I make things work better without making the latency longer if I can? So that's achieved here. And when I'm all done, what I discover is I have throughput. I get one answer every clock period. So even though I can make the multiplication bigger and bigger and bigger, I'm getting one answer every clock period, and the clock period is constant, independent of the operands. So this sticker here, okay, for about the same hardware cost and latency, has throughput that's n times better, this pipeline multiplier. Okay, and the way in which we just structured the problem made it easy to see the pipelining we needed to do to achieve a clock period that did not grow as n. So that's the sort of the purpose of our big exercise. Suppose we said, okay, I'm much more interested in size than I am in throughput. Right? So if you think about our big problem here, is there a way I can think about this pipeline multiplier and say, well, I sort of like it, but I only have a multiplication to do once in a while. Is there a way I can restructure this to somehow get a hardware multiplier that costs much less than n squared? Well, let's think about our problem. So, here we have one diagonal that's busy computing A0 times all the B bits, and this diagonal is computing A1 times all the B bit, and taking the result from the previous diagonal and putting it together, and so forth and so on. Think about how does the problem differ as I go from diagonal to diagonal to diagonal. Well, hardware-wise, it's exactly the same picture, right? I'm just feeding it sort of different generations of data bits, right? I'm taking the results from the previous diagonal and putting in a new A bit and piping along the B bits, but I'm really sort of reusing this one little diagonal stripe again and again and again, and my naive implementation had n copies of that stripe. But suppose I reorganize it slightly and say, look, what I'm going to do is to take one copy of the stripe hardware and reuse it n times. Right? So this is how I'm going to get my hardware savings. Right? Look at the cost now. So we have a one-stage pipeline, if you will. We actually have to run it through n cycles. So the latency is still order n. We have to run it n times. But the hardware cost is now dramatically lower, right? It grows as the size of the operands. It grows as the size of one of these stripes. So here's another EPA sticker, that's on a different model in the showroom that actually has a much dramatically lower hardware cost. I mean, we went from n squared down to n. Okay, and what I've done is to actually allow myself now to reuse my stripe in a way that gets me the same answer. I'm going to take longer to do it. In other words, the throughput now is back to 1 over n, which was the throughput of our combinational circuit. Okay, but the hardware cost is now dramatically lower. Sort of neat, right? We've been able to trade off. We took the fancy pipeline multiplier, which had tremendous throughput, and said, I'm going to trade off some of the throughput for lower hardware cost. Right? So depending on what you want to do. And you say, well, does anybody really do this? And the answer is yes. I'm going to spend 2 minutes talking about a neat example, which I had a chance to work on some years ago. Suppose you're broadcasting a TV signal in the city. So this is sort of the picture, if you looked at the signal coming into your TV set, think of this as sort of one bit of TV picture coming in. Because of all the reflections, what you'll discover is that you get, all these ghosts of the TV bit. So, this is the reflection off the Prudential Tower. Okay, and these are the reflections off of other buildings, and because of the difference in the path between the antenna and your receiver, you're actually getting, lots of different copies of the signal coming in. These are all called ghosts, right? And we, in fact, called this chip the Ghostbuster, because the idea was to do the digital signal processing that's needed to take a very messy signal. Imagine now adding all the different bits at different times together, you can see that the signal gets lost in all this noise. What we want to do is to undo all this. And there's a particular type of arithmetic circuit called a finite impulse response filter, which does that, which involves basically doing a bunch of multiplications. So this circuit needed to do about 150 8x8 multiplications. And 8x8 multipliers are big, much bigger than would fit on that chip. And what we ended up doing was basically building 150 8x2 multiplications, which ran at a 4x clock rate. In other words, what we did is we took advantage of exactly the transformation I just showed you to build a much smaller multiplier and run it 4 times as fast, and then accumulate the partial products in a register, which allowed us to take a chip. This chip, if it was 4 times bigger, would actually be hugely expensive. And so by doing this sort of trading the ability to run at a faster clock cycle, but use a smaller piece of hardware, made a huge difference in whether this was a chip that was alive and well. And in fact, this is circuitry that you can find in most of your TVs today. So it was a fun project. Well, are we done? I mean, here we have a picture. Here's one of our stripes now. And if you think a little bit about how the stripe works, you can see, in fact, we have 4 copies of, again, the same hardware. Right? One of our little individual building blocks now. We have 4 copies of that. Is there a way, for example, in which I could sort of reuse that 1 copy n times to do a stripe's worth of work, and then redo, keep iterating once again to get all the different stripes I need? So this is what's called bit serial multiplication. You build hardware that basically can do, 1 bit of multiplication, and you basically keep track of all the other intermediate results and feed them back into the circuit using registers. And what we can see here is that the sort of ridiculous extremes department is I can get the hardware cost to near constant, assuming for other reasons, I still need to hold all the bits, the partial products and things like that. And often the registers we need to do that are available because we capture the results, the incoming operands and the results going to other parts of the circuit, and we can reuse those registers to remember partial answers as we're busy computing the result over many cycles. The latency is much longer now. The latency is now n squared, because we have to reuse this piece of hardware n squared times. Okay, but the size is really very, very small indeed. So if I put this all together, here's this little table. So this is the comparison shopping that Consumer Reports will put up for you, showing you all the different options you have for buying multipliers, right? We have a combinational multiplier, and you can sort of look and you can say, well, that's in a sense, that was the naive approach, the one that maybe we would have designed without thinking about it. But it turns out there's a lot of trade-offs we can make, some of which are, just sort of better. Like the end-stage pipeline has about the same hardware cost, the same latency, but much better throughput, so forth and so on. So this is sort of neat. This big trade-off that you have to do is the sort of trade-off that most of you, if you go into engineering of digital systems, you'll be spending a lot of time thinking about these trade-offs. Saying, is there a way I can, with the same hardware, perhaps running at a slightly higher clock rate, that I can dramatically reduce the size of the thing? Instead of having an entire rack of electronics to do MP3 decoding, could I in fact make it so small that I could put it in a tiny little device and sell it, put an eye in front of it and sell it for, make the world's most valuable company. So these sort of trade-offs are sort of fun, and they actually have, a real impact on the engineering that you'll do. Okay, good luck on Lab 3 this weekend and recitation tomorrow, and we'll see you next week.